Appreciate it. So thank you so much. It's my pleasure to, to see you here as well. I'm really appreciate your hard working there and all the colleagues that working together to prepare such a beautiful and, amazing international conference. So Dariush Ezrimullah, and I'm Associate Professor of Mathematics in Pennsylvania at Penn State University. So it's my pleasure to be here. And uh, yes, I'm still at my office, but this is, I think, I'm usually at my office in this time as well. So there is no problem for me. I like working, and today I'm going to discuss about the application of mathematics of our an OR for sustainability, which I think that's going to be the topic of this conference as well. So let me just go through the slides and start with the slides. So the world faces challenges in balancing economic progress, environmental. So I can hear myself back. Maybe I don't know. Maybe it's now better. I don't know. So uh, environmental health and human well-being. So social inequalities, resource depletion, and climate change impact our daily life. It's not like before. So nowadays, it really changes anything. So sustainability is truly essential for a long run prosperity without harming future generation. So three fundamental areas of sustainability is environmental sustainability, economic sustainability, and social sustainability. Could, should I stop? I can't hear anyone. So that's something's wrong. So maybe I'm using, let me see if I can use, I don't know what's happening. Maybe I use my headphone to see if it's gonna work better, because I hear my voice back there and it bothers me a little bit. So let's see if I can do this one. Might be better a little bit. I'm not sure if now it's gonna be better. So and something's weird here because I can't. I have to. I can't see you guys. So anyway, so environmental sustainability means wisely using natural resources and pollution reduction. And in economic sustainability means a stable growth without financial crisis. And social sustainability means access to education, fair wages, and community well-being. However, as sustainability is important, without measurement, sustainability efforts may be ineffective. As Lord Kelvin said, when you can measure what you're speaking about and express it in numbers, you know something about it. But if you can't express it in numbers and measure it, so it's not effortless. It's not really meaningful way of improving that. So the data-driven decisions are really essential for sustainable policies. In this case, data envelopment analysis
is actually a tool that, in my opinion, is very useful for measuring sustainabilities and, consider the effectiveness of that. So data envelopment analysis, which abbreviated as DEA, is an operations research tool, usually using linear programming for measuring efficiency, productivity, performance measurement, and it compares decision-making units based on multiple inputs and multiple outputs. So it's a very powerful non-parametric techniques that allows to consider all existing parameters and variables and factors that might be useful for future. So we can consider them. For example, in this case, production plan can be treated as, for example, decision-making units. So it works also on available data, the existing data that we have. So we can, of course, use it for simulations data as well, but in the practice, the data that we provide, that helps us to introduce our decision-making units, and it also cooperates with multiple inputs and multiple outputs, allows to consider a comprehensive measurement. So it's very widely, is applied in economics, environmental, and sustainability analysis. One, for example, work that you may consider it for, the sustainability and data envelopment analysis is the paper that published in 2018 is from Jean and et al. Data envelopment analysis applications in sustainability. If you just, for example, go to the Google and in Google Scholar and write data envelopment analysis and sustainability, you can see a lot of papers coming up. It's a really important area that researchers actually can gain fast, and connect very fast, apply it, in the lots of different measures and contexts, and for any different tasks. And it's also easier to learn it and implement it. And there are lots of good tools also that people can use it. So DA can incorporate economic, environmental, and social aspects of sustainability all together. That's one of the very nice tools that doesn't only focus on one part of that. Of course, it can do. It can only focus on one side of that, but it also considers the comprehensive of that, and it's really rely on a very small number of assumptions. It's not like any other parametric, for example, approaches that people need to care about the assumptions that are available there, like, for example, independent assumptions. You have to care about the homoscedasticity, you have to care about normality. None of these you're gonna be worried about it while you apply data envelopment analysis. As long as you can just divide your data to know which one you desire to have the less value of them, and which one you have the desire to increase them, or you like higher value of them, or even the neutral one. Just if you can classify them like that, you're good to apply data envelopment analysis. It provides insight for policymakers on responsible resource management. It suggests benchmarking and ranking sustainable practices. When you have different practices, you can actually find the best practices. You can find the best one, and then you can benchmark those are inefficient, to using the structures of the best one, that you can identify them and they can follow that pattern to be more sustainable. And it can, of course, rank them. It's one of the fair process of your tools for ranking different units. It can be implemented in all different aspect of programs or methodologies that requires ranking. It's really powerful and it's proven already. So since sustainability is a multi-stage system, so a multi-stage programming also is needed to measure sustainability. So it's not like, for example, since you only consider one part of sustainability. When you only focus, for example, on environmental, you may forget about the economic part and social part. So, but these are kind of linked together. So this is a multi-stage system. As an example of multi-stage system, I just give an example, for example, of a two-stage network DEA that designed for such a multi-stage aspects. If, of course, it can be extended to all different type of systems that we might have, but this is one of the basic um, typical two-stage network DEA. As you can see, it has two stages. The first stages, as you see, it's like x1j, x2, xmj is multiple input values that we might have. So these are parameters, factors that we consider them as input or resources that basically, like, cost benefit, like cost revenue modeling, we like to decrease these value, or these values, the smaller values of these parameters are more desirable. And then stage one, when it's applied, gets these inputs and provides some intermediates, we call them, which is the output of the first stage, that here is shown by Z1 to ZD. That means you have multiple also intermediates as Z1 to ZD. And then the output of the first stage gonna be treated as the input of the second stage. And the last part is the outputs that's shown by Y1 to YS, which is, again, you can see it's multiple outputs. So it's not like, if you remember the regressions analysis, even in multiple regressions, that when you apply it, it considers multiple, for example, parameters, and it's for only one parameter as a predictor. Of course, you can consider also different type of, but like regressions analysis, you can expand it also for multiple output as well. However, the problem that we have is that it needs a lot of assumptions to be checked before we apply that. But here we only need a very few assumptions, as we discussed. So inputs is given to the system, and intermediates is given, which is the output of the first stage. It's gonna be the input of the second stage and the output of the last stage. So the entire system gets some input and gets some output. We can actually expand this one for the sustainability measurement. Like, for example, we can say environmental efficiency. We can assume, for example, energy consumptions and carbon emission as our input, and eco-friendly innovations or waste reductions as our output. That's for the first stage of sustainability. In economic efficiency, we can consider, those output that we already have and add some more also input as well, like eco-friendly innovation or operational cost, for example, that we have, and then profit and productivity as the output of, economic efficiency. Or in case of social efficiency, we can consider, for example, income inequality as our input, and employment rate or social inclusions as our output. So we can actually design this, task, and then go and measure the sustainability. So data envelopment analysis identifies inefficiencies across multiple states. It actually gives a score between 0 to 1. Those 1 shows those efficient one, and when it's less than 1, it shows the inefficient one. So actually each unit or production plan or decision-making units, they know how far they are from the efficient to be efficient, and how they can regulate their data or their inputs and outputs to be more efficient. It provides really comprehensive sustainability assessment, and it supports data-driven decision-makings for sustainability. So in sustainable agriculture, for example, we can apply it, in agriculture. We can evaluate, for example, land, water, and fertilizer uses, and etc. These are could be all the parameters that we can implement it to a data envelopment analysis model and then apply it and find the result to improve the efficiency and productivities of our agriculture. In industrial efficiency, for example, measuring economic output and environmental impact, or in urban planning, assessing, for example, sustainable infrastructure projects. So there are lots of good ideas that you may also come with that while you're trying to work on it, and it's really also nice. And it would be, there are lots of also journal publication, journal papers that you can also publish based on these work. So sustainability requires balancing economic, environment, and society. So it's a multi-stage task, and DEA is actually provide a robust tool to measure and improve efficiency. So network DEA helps analyze complex systems and derive informed policies. So this is also, as I explained later, before, it's one of the works that you can start with actually and then move on to other part of the sustainability. So as I discussed, DA offers a promising path for sustainability research. Researchers can apply DA in varieties field, supply chains, energy transitions, urban planning, and so on. Collaborations can enhance methodologies and solve also sustainability challenges. And I'm offering my help also for any young researchers or even, senior researchers as well. If they really want to work on this topic, I'll be happy to collaborate with them. I'll be happy to involve with any, research, PhD research, or, just for a grant proposal, to apply for that. I'll be happy to help. I will be happy to, work on this area with you. It's been about, I started, working on data envelopment analysis in 2011, and it's been about maybe 14 years I'm working on this area, and I, loved every single days of that I'm working on this area. So I really love what I'm doing. And if you see me now, I'm still at this. I'm at my office until this time. This is my daily routine. I'm doing it all the time, and I've been here since early morning. And then usually after midnight I gonna go home. So that was my talk I provided for this conference. I hope you like it. I try to avoid math part of that. It has, of course, it's linear programming, has a lot of mathematics in it. So I just thought maybe in general form that might be more useful, that I share these informations with you. This is my email address. You can always find me here if you want, and I'll be happy to have any collaborations with you. So thank you so much for your attentions, for listening. And if you're any questions you have, you're welcome. I'll be happy to answer if I can. Yes, I can now. I can hear you. Barely I can hear you. Thank you. Could you hear me? Because I didn't know if you guys can hear me. You're welcome. I'm sorry I couldn't hear. I can't. It wasn't clear. I can hear you, but I couldn't get your question. Yes, absolutely. Absolutely. That's actually one of the area that I'm working on it. I'm trying to develop actually those models. There is a very, very, large literature on healthcare and data envelopment analysis. There are actually a book about it. If you just search healthcare data envelopment analysis, a variety, uh, models and studies, you can find them. And what I offered here is that uh, it doesn't matter if actually any area or topic still use data envelopment analysis or they haven't used it. If there is a passion about it, we can create actually the models and use it on that area as well. I think it's very strong uh, tool that can be applied in all different aspects and area. You're welcome. Yes, please. Good morning. Very nice to meet you. Yo, absolutely. Actually, uh, if you search it, actually, Penn State, we actually collaborating with some Indian universities, and they actually last semester came here and visited us. I actually make some good friendship with them. Somehow they like me, so and I like them as well. You know, so it's it's been let me. So I just noticed that I have to turn off the presentation. So yes, so so yes, so I believe we actually. Thank you. You're welcome. Thank you. Perfect. That would be awesome. I'm looking forward to it. You're welcome. Take care.
Yes, sir. Yes, sir. I am here. Yes, sir. Just recently. Thank you. So good to see you after so many days, sir. Thank you. Thank you, sir, and respected audience and guests. I'm very pleased to join this prestigious event online, and I was very carefully listening to Dr. Daryush and his insightful discussion. I had prepared something for this conference, but because of having a lot of pain in my throat, and I was almost unable to talk when I got up in the morning. But somehow, having some hot water and some medicine, now I could at least talk. So, with this disturbed voice, I will not disturb the respected participants here for a long time. But I thank Professor Subudhi sir and organizers for this wonderful gathering. and hopefully someday I will personally able to join this conference and meet you all personally. I hope a very successful organization of this conference and best wishes for you all. Happy conference. Thank you. Thank you, sir.
Yes, hi. Yes, hi. Hi, everyone. Hi. I wanted to present my talk. I never use the software, so I'm not sure how to share my screen. Uh-huh. So how to share my screen? How to show presentation? Uh, uh-huh. Mm-hmm. Reaction present. Maybe present now. Ah, Let me share my screen. Uh, yes, can you see it? Okay, okay. All right. Okay, okay. So today I want to present um, the talk which I called Invariant Solutions of Nonlinear Modeling. And I will not talk about many things, but I decided to, just a second, I will put just this part probably. Uh, so, uh, just a second, we'll try. Yeah. So I wanted to discuss exact solutions of Navier-Stokes equations that are used to describe atmospheric motion on the surface of rotating spherical shell. So if you consider Navier-Stokes equations, uh, so this just complete Navier-Stokes equations. So just written in vector form, where nu is viscosity, delta is Laplacian, and the term here, dot product with angular rotation, describes the Coriolis effect, the rotation of the Earth. So we consider rotation of the Earth as spherical geometry. So the Navier-Stokes equations can be reduced from three-dimensional to two-dimensional equations on the surface of a sphere if we show that a velocity vector is corresponding to two components, two angular components. So we ignore radial component of velocity. So in two dimensions, in spherical coordinates, the Navier-Stokes equation is written in this form. So I just wrote completely the whole equations here. So the function f here, the perpendicular theta, can be used to describe this kind of heat wave on equator. And delta s is this linear operator. So the question is how to solve these equations for d theta. It's a one angular component of velocity with phi. Another, yes. Oh, I'm sorry. Can you? Okay, okay. I will do this way. Okay, so basically we consider two-dimensional Navier-Stokes equations for v theta defines two velocity components and pressure P. So Re means Reynolds number. It's a number responsible for viscosity. Delta S is this operator. F here is a function of theta, which is used to describe heat equatorial waves. Um, What else here? Uh, R0 is a Rossby number which is responsible for rotation of the Earth. So question is how to solve the system of equations for three unknowns, v theta, v phi, and p. So independent variables are t, which is time, theta and phi, two angular components. So basically, I just use invariance principle here and found transformations that leave equations invariant. I just wrote these transformations in terms of differential operator. So we found 1, 2, 3, 4, 5, 6 transformations written in terms of differential operator that leave all equations invariant. And based on this, for example, for operator x4, the transformations of dependent and independent variables can be written this way. So it's transformation for time, transformation for theta, one angular velocity, and transformation for phi, it's another component of angular component. And psi is a stream function. Because equations are two-dimensional here, because equations are two-dimensional, we can always introduce stream function. So instead of v theta, v phi, we can just use a stream function. Yeah. Yeah. It's a transformation for the dependent variable psi. And beta is just some arbitrary constant. So based on these transformations, we can find exact solutions of Navier-Stokes equations. These are completely non-linear equations, but we can find exact solutions. So I just wrote this way. So for v theta, for v phi, it's one exact solution, and v theta 2, v 2, and p2, it's second exact solution. I didn't write p1 because it's just long expression, but we can also write p1 as well, where f is a new function and lambda is this function. So basically, there's two exact solutions with index 1 and 2 represents exact solutions of Navier-Stokes equations. And f is minus sine theta divided by 2r0. So basically, these exact solutions were never reported in previous studies. And how we can obtain the solutions? Again, by using invariance principle. So we find transformations of dependent and independent variables, which are here written. So dependent variables v theta, v phi, p, and independent variables t, theta, phi. So we find transformations of dependent and independent variables that leave equations invariant. And as we indicated here, we found 1, 2, 3, 6 transformations. So based on these 6 transformations, we can find two classes of exact solutions. Exact solutions. And one of the questions here is to investigate the asymptotic analysis of energy balance associated with exact solutions that we obtained. So these energy balance equations, for example, if S equal to 0, that will be energy conservation law. If S is positive, it's a source, and if S is negative, it's negative. It's a sink. And S is given by this expression. And again, since we have found exact solutions, we know what is S because V is known, V theta is known, V phi is known, F is known, everything is known. So basically, it's known function now. And actually, we found interesting observations that S1 are the S a source function for the first invariant solution. So for the first invariant solution here, it's identically equal to 0, which means that first invariant solution always provides energy conservation law. However, the source function, which is here, source function. For the second invariant solution, which is here, for v theta, v phi, and p. For second invariant solution, it's not equal to 0, but it's asymptotically approaching 0 when it's approaching to infinity if f equal to this function, and S2 approaching to some constant value if f is arbitrary function of theta, just something else. But for this particular case, it's approaching identically to 0, which we can visualize graphically. So, for example, if f equal to minus sine theta divided by 2r0, and here's another f, which is, I just choose randomly as 100 divided by sine theta, something else. So let's see what happens with source function at initial time, not initial time, I just started 0.01 to ledger time, so it's some kind of animation here. I need to share screen a little bit here. Probably I will do it this way. I don't know if you can see it, but can you see the animation? Well, basically, it's just, I will remove it. So you see, if we start source function, somewhere it will approach to 0 asymptotically. However, if f is something else, it will approach to some constant state. So another problem which I wanted to, how much time do I have? Do I have some more time, or it's okay? Maybe 5 more minutes. It's another problem on ocean whirlpools. So basically, we can start with a mathematical model describing internal waves in fluids, which are confined in this kind of cylindrical domain from 0 to h with radius r0. Plus, we have two boundary conditions saying that the water is not coming out of cylinder from a side and also not coming up and down, so it's confined in cylinder. So we can solve these equations. So first thing what we can do, we can linearize these equations and solve linear model numerically by showing that boundary conditions provide some points for which solution is valid. And I just will show you here. So basically this would be eigenvalues of the problem at which solution is valid. And solving these equations for linear model, we can also write our energy balance equations, which is written in this form. But we are mostly interested in energy density. So this part is not very important. And here we can find solutions of internal fluids. In polar coordinates, it shows some kind of whirlpool motion, which we can also observe in atmosphere for linear model. But also we can show that a radial component of velocity asymptotically approaching to 0, which means that we can solve nonlinear problem assuming that UR, which is UR is written here, we can say that radial component of velocity approaching to 0, which means we can hold nonlinear problem in which UR can be replaced by epsilon UR, where epsilon is a small value, assuming that, saying that UR is not 0, but it's very small value. And actually we can solve nonlinear problem, completely nonlinear problem in first order, again using Lie group analysis invariant principle, finding transformations of these equations and find exact solutions of this problem. And exact solutions can be visualized as this whirlpool, in which pressure is 0 on the surface of the cone, pressure is negative outside, of the cone and pressure is positive inside the cone, which actually corresponds to physical description of real hurricanes. So basically, this solution can represent a hurricane of internal associated with internal waves. And we did some other projects about it, about stability of whirlpools, but probably I'll stop at this point. But the key point that using transformation principles, we can solve exactly nonlinear equations in many situations. I basically just considered two models, but we have much more applications of invariance principle. So basically, I want to stop at this point. So do you have any questions? Ah, yes, yes. Uh, uh-huh. Okay. Uh, yes, it's an echo. I don't hear very well. But can you hear me? Yes, yes, yes. Can you type something in messages because of the echo I cannot hear. Oh, thank you.